but I will go over that again. We have here buckets A and B. Water comes down from above. Water runs through. You see the water there, runs out. And we collect these water drops here in bucket D. It's a conductor. And this water is collected in bucket C, is also a conductor. And the paint can A is connected to C, that's crucial. And the paint can B is connected with D. And here there are two balls which I can bring close together. I run water, and after a while I see a spark here. I can even see a spark when the distance is something like 6 millimeters, which would be about potential difference of about 20 kilovolts. How does it work? Well, water has a pH of 7, and that means 1 in 10 to the 7 molecules is ionized. So I have OH minus, and I have H plus. And those are going to be the current carriers. The ions are doing the work here, are doing the job. Let us make an enlargement here of can A. And can A, let us assume that purely by chance, it has a little bit of positive charge on it. It could be negative, but I'll just assume it's positive for now. In either case, it will work, you will see. Just by chance, like you have a little bit of net charge. You're not completely neutral. And so this can has a little bit of positive extra charge. And now here is the drop from the spout. What's going to happen? Through induction, through polarization, you get a little bit of excess negative charge here and a little bit of excess positive there, because the positive repels each other and the negative is being attracted. So the H plus goes a little bit up and the OH minus comes a little bit down. But now the drops breaks. And here goes the drop. So it's a little bit negative. So now a little bit of negative drops come down, and so this becomes negative. But this is connected with B, so B becomes negative. But what do you think is going to happen now with the drops that fall through B? They are going to become positive. Because if B is negative, then of course this will be reversed. The bottom will be positive, the top will be negative. And so those drops now that are going to fall through are going to be positive. So C becomes positive. But C is connected with A. So A becomes more positive. And so A can do even a better job now on these water drops and polarize them even more. And so you get a runaway process. And the whole system feeds on itself until the potential difference here becomes so high that you exceed 3 million volts per meter, and then you get a breakdown and you see a spark. Now you can think of a continuous stream of water as a stream of individual drops. So it also works if you just have a regular stream of water going down. Who is doing the work here? Someone has to do the work. You have a battery. The battery is being charged, and then it is discharged through this spark. Who is doing the work? Any idea? Have you thought about that? Yeah? Gravity. Very good. It's gravity that is doing the work. We can see that very easily by identifying the current that is flowing and the electric field. How is the current flowing? If negative charge is going down, would we all agree that the current is going up? If positive charge is going down, do we agree that the current is going down? This side of the spout here will be slightly positive, and this is slightly negative, because the H plus is more abundant here than there, and so we're going to get a current through the water in this direction. The current has a reasonable conductivity, because it's ionized 1 out of 10 to the 7 molecules. And so once in a while, if you see a spark here, then you get a current there, but that's intermittent, of course. How about the electric fields? Well, electric fields, we know, go from plus to minus. So that's easy. We can put the electric fields just in like that. Electric field must here be in this direction. The electric field here goes from plus to minus. C is plus charged, B is minus charged, and so the electric field is in this direction. Electric field is from plus to minus. This is plus, this is minus, so the electric field is in this direction. Electric field is from plus to minus. The can A was positive, remember? So the electric field is from plus to minus. So that's the electric field configuration. But now look what's happening. Here, the E field and the current are in the same direction. That's fine. Here the E field and the current are also in the same direction. That's great. But now look at these poor negative ions. These negative ions don't want to go in the direction of E. Negative charge wants to go against the direction of E. But gravity says, sorry, you can't do it, I force you down. And so these negative drops are forced by gravity to go down. Look at this positive charge. These poor water drops, which are positively charged, go against the electric field. They don't want that. Positive charges want to go with the electric field. Gravity says, sorry, it's too bad, I force you down. And so gravity is doing the work, so to speak, against the will of the charges. And then the battery charges up and charges up until the potential difference becomes so high there that you see a spark, and you deal with potential differences of something like 20 kilovolts. Remember last time, and you will see that again today, that as the water goes through and as the system charges up, that you begin to see that the water, which starts running like so, begins to spread out. It fans out. You could hear it by a change in the sound, but you can also see it, and I'll make you see it again today. Why is that? Well, that's immediately obvious. If this can is positively charged, but if the water is negatively charged, the negative charge wants to go to the positive can, and so it spreads out. So it's clear that by the time that you reach almost the spark, that water will spread out quite substantially. And you will see that. And then when there is a discharge, it will start running again, narrow stream, and then slowly in time, the water will spread. And so now I will do a series of demonstrations which will support what we know and what we perhaps don't know. Let's first give a little bit of light here, because we will need that. And then I'm going to make it completely dark so that you get maximum pleasure for your money. And I will first show you here the gap, those two balls. And this time we have a real treat, which we owe to Marcos, who is standing behind the instrument very modestly. This time we have a gauge, a meter, which measures the electric field very close to can A. And the reason why that is nice is that as this system charges up, we just don't have to wait now just until we see the spark, but we can look at the galvanometer there and slowly see it being charged up. And then we get a spark, and then it discharges. So you get a lot more for your money. So I propose that the first thing we do is what we did last time, that we simply let it run and see whether we get a spark. There's always air bubbles in the system, which I have to get out. Okay, I think I did that. Okay, let's just be patient. Ah, it starts already. Look at the E field. Bang! First spark. Can you see the spark on the screen? Look at it again. There's the spark. And at the same time, you see how the electric field goes away, charges up, bang. Charges up, bang. So it starts the whole system charged because of a random positive or negative charge that would be present on one of the cans. What I want to do now is I want to increase the gap between the two balls, and I make it so large that you will never achieve an electric field there of 3 million volts per meter. But somewhere else on the unit, it has lots of sharp edges and sharp points, somewhere else the electric field will reach the breakdown voltage, and so the system will go into discharge, into corona discharge. You will never see sparks, but it goes into discharge. And you can see that because now, I will open the gap now. If you now look at the electric field, it will reach a maximum value, and now it goes into discharge, you see? It begins to sort of sputter a little bit back and forth. So now there is no longer a spark on the balls. You don't see anything between the balls, but it is somewhere else, I don't know where there is a continuous stream now of charging leaving the system, and so it's discharging to corona discharge. And so in this mode, you expect the water to be spread all the time. And I will show that to you by switching now to the water. Maybe, Marcos, you can improve on the light. I could turn this off, maybe you'll see it better. But you see that the water is spread, and I will now bring the two balls closer together. You also want to see, of course, the electric field to see the discharge. So I bring them closer together, stopping the corona discharge. There's a spark. And now watch the water. See, the water is now just not interesting, and there it spreads. I'll turn the light off. You look at the water. So slowly the system is charging up. You see the water? Bingo. You can even tell by the water when it sparks.